All right. You know, I realized today that I hadn't deleted files from a while in that camcorder, so there's a chance this will actually not get recorded today. I think I tried to delete them right now, but the interface on that thing is kind of a pain. All right, anyway, so hopefully, I guess you're all here, it doesn't matter, but the people listening, if it cuts off midway through, I apologize. Hopefully people are coming here in general. So today, my pen. Didn't write the little intro before, but I can do that now. Okay, there we go. Today we're going to start off talking about, first of all, the homework, actually. So the first homework is posted on the website. I do see some new faces here, so there may be the website I think everyone should have, right? But otherwise, talk to me after class. I think there was some mix-up where it wasn't posted on the course listing, so just talk to me at the website or talk with anyone else. The first homework is on the website. So it is due 2 weeks from today at the start of class. The homework has several problems that are marked as being for the 884 class only, and the rest are for the 484 and 884. Now, having said that, what I found was that a lot of people were dropping out of the 484 and entering the 884. Hopefully the homework will be, and I understand sort of the reasoning for that. I mean, you sort of want to do the harder level course, you want to do the original research, that's all great. Hopefully the homeworks will be a gauge of whether or not this was the right call or not. The homework, I'm spacing it out, so it means this is a 12-unit or 9-unit course for, so that's the number of hours on average, amortized over the entire semester you should spend. So the homework, given that the homework should take you between 15 and 20 hours to do. Each one, we have 4 of them, they're spaced out, and you also have the project as well. Maybe more towards 15. If it's taking you much more than that, come talk with me, because it might be that you should switch to the other one, or if it's taking you much less than that, I guess that's great, maybe you should switch up if you're in the 484. But if it's taking you a lot less than that, I mean, I do want to stick with the units that are required for the course. I don't want you spending 20 hours per week on this course. And so if it's taking substantially longer than that, come chat with me. We can either maybe give you some background reading or something like that that might help fill in some of the stuff you might be missing, or we can chat about switching. If you have kind of administrative concerns about switching, come talk with me too. I think we can work out all those things. Like if you need the different numbers of units or whatever, we can make all that work. Or if you want to do a research panel project, we can make all that work. But do come talk to me and we can then work it all out, because I don't want you spending 30 hours per week on the homework. Having said that, the homework is meant to be hard, right? So it's the number 2 weeks, or you're supposed to spend between 15 and 20 hours on it. So it should take you some time to do. And that's a good thing if it's taking you some time to do. The other thing is because of that, please do start early. I know everyone says this, but at least take a look at it within the first week or so. Take a look at it, download it, and see what the problems are. You have to download some data too, so make sure that all works, that you have MATLAB set up, all these things kind of work, because if you're doing that all the last minute, that's going to be a really, it's going to be a headache, and you probably have to use your late days on the first assignment, and that's not very good, because trust me, you'll be more busy at the end of the semester than the beginning of the semester. So are there any questions about the homework? There's sort of I know no one's looked at it yet, probably. I just put it on half an hour ago, but if there are any questions about kind of the logistics side of things. Okay, so the first homework covers up through nonlinear regression. That's why I wanted to wait till today to actually give it out, but it doesn't go any further than that. So what we learned today will be enough to do all the homework, basically. All right, now today in class we're going to talk about 2 things. We're going to first of all finish up nonlinear regression, and finish up nonlinear regression using kernels. So at the end of the class last time, I introduced kernels. It was a little bit of a whirlwind, I know, because there was lots to sort of take in. So I'm going to go through that again a little bit. and kind of remind you what we covered last time, and then finish up and sort of talk about not only how do you optimize with kernels, but how do you maybe use alternative loss functions and things like this? How do you use alternative loss functions? How do you make predictions on new examples if you don't have this data vector stored precisely? So we'll go through all of that. And then I'll switch gears a little bit and talk about a different kind of machine learning problem, though they really fundamentally aren't that different. But this is classification problems. In regression problems, the thing you're trying to predict is a real valued output. Remember, we're talking about, in this case, at least single valued output. So it's a real valued number, a scalar value you're trying to predict. And that makes sense when we're talking about something like demand, which is a number itself. And it's sort of a natural order, right? So maybe there's some sort of smoothness here where if the temperature goes up a little bit, you might expect the corresponding output, peak demand, to go up a little bit as well. Classification is a different problem. Classification is a problem where you're trying to predict some number of discrete outputs. And this can be very useful because sometimes the questions we want to answer in machine learning problems are more like yes or no questions, right? We have some problem and there's a yes or no answer. You know, should we shut down this power plant or not? Is it going to fail? Is this device, and I'll use some more examples, but it seems like, is this device that's turning on right now a refrigerator or not? These things are not things where you can say 0.1, 0.2. You want to say yes or no. You may want to say probabilities too, but really fundamentally the answers there are yes or no answers. And that's the domain of classification here. So that's what we'll talk about in the second half of the class today. We probably won't finish it today, but we'll at least get well into it. So first of all, were there any questions about kernels from last time? As I said, I am going to jump in a little bit more, or rather go back a little bit more and kind of rehash what we learned. But were there any questions of what was happening at the end of the class last time? I derived essentially least squares for the kernel, for this kernel representation. Everyone perfectly understood that. Yeah.
In representation difficulties, you talked about overfitting. So could you explain that?
Yeah, so overfitting, I'll talk a little bit more about when we talk about evaluating. I'll define it more formally when we talk about evaluating machine learning algorithms. But informally, the picture to have in mind from overfitting are stuff like this. Actually, let me first do this one. These are the pictures to have in mind when you think about overfitting. What overfitting is remember, we're talking about minimizing a loss function on a fixed number of data points, right? So if you add more and more features and keep the number of data points the same, your representational power gets bigger and bigger on those data points, right? Because you have, to the point where if you have 1,000 features and 1,000 data points, the features are all independent actually, you can get perfect predictions. Under certain assumptions at least, you can get perfect predictions on those outputs because it's just about inverting a matrix. Really all it boils down to. The point here, which I'm making a little bit intuitively now, rather than trying to give sort of mathematical definitions, is that this is not necessarily a good thing, right? Getting low loss on the examples that we are given, that is great. But that's not kind of the be-all, end-all of machine learning, right? In some sense, and again, I'm making this all a little bit informal now, but in some sense, we want it to perform well on all examples, right? Not just the data we give it, but on everything. And so that's what these kind of pictures show. So here we show the x's are the actual data points we have. And the red line spans through kind of all the possible inputs. Okay? So for this function down here, what's happening here is that we are going, for example, on this data point, we have zero loss on this data point. Our function is like this, and then goes up and has zero loss here, right? But I would not call that a good function, because right next to it, here, it's really bad. There's no reason to think the function actually looks like that. So this, at least informally, is the picture to have in mind when you think about overfitting. What we're doing is, in order to fit the data that we see, we're coming up with some crazy function. And we can fix that in two ways. We can either decrease the number of features. This has 50 RBF features. We can decrease that. That's what's sort of showing here. Here's with only 4 of them. It looks like a much better fit. or we can add regularization. Regularization is a penalty on the weights, which acts very similar to decreasing the number of features. So that's the intuition behind overfitting there. Okay? All right. So is that sort of explaining the answer to your question? Okay, great. So where we left off last time is that I was talking about two ways to use nonlinear features, to capture nonlinear features. So we can have very expressive functions that we're fitting to the data. The first way was, as I said, just building the features. I'm calling that explicit feature vectors. That's the first thing we can do. The second thing we can do is construct them implicitly using kernels. Right? And this was sort of this whole area called kernels in machine learning, which has, again, become very popular in the last 15 years or so. So I defined a kernel. Maybe I'll go back even further. I defined a kernel function as being the inner product, okay, of z and z prime. Z and z prime are both two different inputs. This is the inner product of some set of features describing this guy. And what's very nice about kernels is that to compute this inner product here, we don't actually have to construct the features themselves. Turns out, I mean, you can't get any feature this way, certainly. If you define some feature, some random feature, that's not necessarily going to be a kernel for it. But for a lot of kernel functions here, for example, if we were to take this polynomial one, where we just define this as 1 plus z transpose z prime to the d, for a lot of functions like this, those are actually working in an implicit high-dimensional feature space. So what this is actually doing, as we saw last time, right, was computing inner products in a high-dimensional polynomial, a d-dimensional polynomial of these inputs. Right, but we do it without ever actually forming those d-dimensional polynomials, which can get very big very quickly for reasonable size dimensional inputs. Similarly, this is called a polynomial kernel. Similarly, we can form a Gaussian kernel, which looks a little bit like the RBF function there, but really it's the difference between the two input points. We look at the difference between the squared L2 norm between z and z prime, divided by some number here, and that's our kernel. Again, that's easy to compute, right? We don't have to expand any high dimensions here. As I said, we're not going to prove this, but that actually corresponds to a feature vector that has a radial basis function at every single point in space. It's actually like a feature function, because it's actually an infinite value, infinite size feature vector. So this is sort of the introduction to kernels. Kernels are a way of computing these high-dimensional dot products very efficiently. But that doesn't really quite solve our problem yet, right? Because, well, that's great. We can compute inner products. How do we actually, do machine learning algorithms? And that was what we came to last time. So for this, remember, we used this property called the Representor Theorem. The Representor Theorem says if we have an optimization problem like this, minimizing some loss function plus some regularization term, and that really is kind of, as we'll see for both regression, certainly, but then actually even for classification, it turns out, too. This is a very general formulation, and a lot of machine learning problems just are formulated like this, and this is exactly the thing people try to solve. So that's a very powerful sort of formulation here. It's very general. If we have a problem like this, and we're solving for the best theta there, then the best theta, the optimal theta, has this form. The optimal theta is actually a sum from I equals 1 to n of some weights alpha i's times the feature vectors evaluated on the inputs. Okay, and again, these are not infinite dimensional, really, really high dimensional here. So obviously, theta has to be the same size as our feature vector, right? That's how we're defining it. Our function is, we're predicting is theta transpose times the feature vector. This is going to be huge. We can't even store this in memory. These are all going to be huge. We can't store them in memory either. I'm just telling you this fact because we're going to use it. This is some linear combination of these. And the reason why that's nice is that we actually then, in some sense, to represent this, we don't need to actually store the whole vector. All we have to store are these weights here on each example, or each feature vector. That gives us a way of storing this high-dimensional vector here without ever actually storing it in memory explicitly. Now, I think I might have done it in a little bit of the flipped order intuitively last time, but let me go to skip ahead, because the next thing I did was sort of define essentially least squares regression like this. But let me actually do something else first. So suppose we have a theta that's represented like this. Okay? And then along comes some new input, x prime, which is, again, x prime is, remember, in Rn, but phi of x prime is going to be in Rk, and that's going to be really, we're going to assume k is really, really big here. Okay? So how do we actually make a prediction on this new guy? Remember, our prediction, y hat, I'll call it y hat prime just to say this is the prediction on the new input, this is going to be equal to theta star transpose phi x prime. Okay? Now here's the sort of the fun part, right? Is that, well, we know from our definition here, let's plug this in. These are both too high to store, of course. We can't actually write these down. But what we can do is plug in our sort of compact representation here. So this is also equal to the sum from I equals 1 to m, alpha I, phi xi, this whole thing transpose, but I'll actually just distribute this in. Actually, yeah, this whole thing transpose times phi x prime. But I'll just move these things inside to make it a little bit easier here. Move the transpose in here, and I'll move the phi of x prime inside there. Okay, so that's what this prediction is. And now hopefully it's apparent that what's nice here is that this is all about inner products, right? This is just an inner product here. So this is also equal to the sum from I equals 1 to m alpha I times our kernel function, k of xi x prime. Okay, so that's how we actually go about making predictions without, and remember here, this just involves this function. We can evaluate this function. This is, easy. Well, I erased it, but this is easy to evaluate for any 2 points here. And we have to know our alphas. So as long as we have that, then we can make predictions here without ever storing theta or any of the phis. So now all we have to do, of course, is find these alphas, right? We want to find the alphas that actually solve this problem. That's actually what I just finished on the end of class, at the end of class last time. But let me go through it again now that hopefully this makes a little bit more sense about what you do with these alphas once you actually get them. Are there any questions about this part here? Okay. You're sure? All right. So now let's go back and talk about how we actually find the alphas here that actually give us theta star. All right? Okay, so this is that derivation I showed last time. But I'll go through it again just because I think it's probably worth going through more than once. Our function we're trying to optimize, remember, j of theta. We want to minimize over theta, j of theta, which here is equal to, I'm just going to go ahead and use our notation from before. So phi is a big matrix with the rows being each phis. Forget about the fact for now that you can't actually store that. You can't store it because it's too big, right? Each row is very, very high dimensional, wouldn't fit in memory. But this is equal to phi times theta minus y. You can't fit theta in memory either, by the way. So we have two things that are too big to ever store. That's not that good. But remember, our kernel substitution said that said that theta, at least at the optimal, and let's just worry about what we can do at the optimal here, because we don't really care about other points besides the optimal one here. So the theta star was equal to the sum, I also went to m alpha I phi xi, which another notation, I'm going to use my matrix notation now, this equals phi transpose times a vector of all the alphas, right? Remember, this matrix here has, or rather phi has the little phi's transposed as the rows, so this one will have phi's as the columns, so it's just a linear combination of all the phi's. So that's just the sort of the definition of vector matrix multiplication here. It lets me do that transformation. So let's now go ahead and plug this in. So this equals phi transpose alpha minus y. And, as I showed last time, the matrix phi transpose, remember this is going to be an m by k matrix. This is a k, therefore a k by m matrix. This whole thing is going to be m by m. And I'm actually going to abuse notation a little bit here and call this also k. And k is a matrix where the ij value of k ends up just being the kernel function between xi and xj. Because this is just a matrix of all the possible inner products here, which end up just being kernel evaluations. Okay, so I'm going to use this now, the fact that phi transpose equals k. I'm going to plug it in. Oh, I should also say I'm adding regularization too. I'll plug this in, and I'm actually going to write it like this. So remember, this term is equal to lambda theta transpose theta. So this is then equal to this plus lambda times, well, you have alpha transpose phi transpose alpha, again, with our definition of what theta is here. OK, so now our problem is to minimize this thing. And we're minimizing over theta, but really we've substituted in alphas here as our, what defines theta. So we're going to minimize this thing over alpha. And that's going to give us the optimal set of alphas that we're going to use to then make predictions. OK, so now we have to do the same thing we did for least squares. This function turns out to have an analytical solution. Meaning you can solve for the best alpha just using our rules of gradients and setting those equal to 0. So let's just go ahead and do that. Let me erase this here. So let me erase all of this here because it might take me a second to write this. OK, so first of all, and I guess I'll just write this as this, remember, equals k alpha minus y squared plus alpha lambda alpha transpose k alpha. OK, now let's go ahead and first distribute this out a little bit. Remember, this thing here is just the 2 norm squared is equal to this term transpose times itself. So this is equal to k alpha minus y transpose k alpha minus y plus lambda alpha transpose k alpha. OK. Let me just write these terms out then. I'll just distribute out the multiplication here. So this is just going to be alpha transpose k. It's k transpose, but k is actually symmetric. Doesn't matter in a kernel function if you evaluate x, I, xj, k of xi, xj, or k of xj, xi. Those are the same thing. You should check that for all your things here, but kernels actually have to have that property. So this is going to be a symmetric matrix. So it's just alpha transpose k, k, alpha minus y transpose, 2y transpose k alpha plus y transpose y plus lambda alpha transpose k alpha. Just writing this thing out distributing out like that. Okay, now we want to find the solution to the alphas that minimize this function, right? To do that, we take the gradient of it with respect to alpha and set that equal to 0. This ends up being the exact same rules for our gradients as we had before. So what we have is the gradient of this whole thing with respect to alpha. I won't write the whole thing, but just gradient of this thing. I guess I'll write it like maybe j of alpha. Equals, okay, let's just play our rules now. This is the setting of, the thing we're taking gradient with respect to times some matrix times that. So it ends up being just this matrix times that, and it's actually times 2 because this is symmetric here. So 2 times k alpha minus, well, we have this thing times that, so it's this thing, whatever the transpose of this thing is. So we have minus 2 ky. This one here does not have alpha in it, so it's 0, the gradient. And finally, this one is the same form as over here, just with only 1k. So this is going to be then plus 2 lambda k alpha. And we're going to set this whole thing equal to 0. Everyone following this step here? What I did here? Okay. So now we have an equation. We want to solve this equation for lambda. Well, let's first actually simplify a little bit, and let's multiply by the inverse of k. We have a lot of k's here on every term. Let's first just multiply by the inverse of k on both sides. So it doesn't affect this side. I should also say there is a possibility that k will not be invertible. For some kernels, it's not. But it turns out that in this case, at least, it doesn't really matter because everything is sort of pre-multiplied by k. So if, let's see, so this is sort of k times this thing, right? Maybe actually I should better write it like this. So this is k times this thing, 2k alpha minus 2y plus 2, I'll write it like this here, 2 lambda alpha. So this thing should be clear. This whole thing is equal to 0 if this thing in the middle is equal to 0 too, right? So even if k is not invertible, if this thing is equal to 0, this thing will also be equal to 0. This whole thing will be also equal to 0 because you're multiplying 0 times the matrix k. That's still 0. So let's just go ahead and make this thing equal to 0. Okay, so let's first, all these terms involve alpha except for this one. So we have 2k alpha plus 2 lambda alpha equals 2y. All right, first of all, let's get rid of the 2's here. So what's the solution here? What does alpha equal? I'll write it like alpha star equals. You want to tell me? It's up there too, but can you just derive it from here? K plus what? Yes. This is equal to k plus lambda times the identity. Important, the identity there, not just k plus lambda. Inverse times y. Okay. So that's how we compute the best lambdas that actually give us the solution to this problem. Now, if you think about it, this is actually sort of a pretty surprising thing, right? We can actually do these high-dimensional, use these high-dimensional feature vectors without really paying the price for it in some way, right? We're never actually forming them. We just have these really high-dimensional feature vectors. That's pretty nice. It's not completely free, this power we have, right? Because you still have the representational problem. You still, if you have if you have not many data points, for example, and you want to use a really high-dimensional feature, you're still going to overfit to the data. You're going to maybe have to use, a high value of lambda to prevent that or something like this. But this is still a pretty kind of impressive thing that we can actually come up with both the solution to the optimization problem and make predictions on new examples, all without ever forming these big feature vectors. Okay, so the other thing I want to sort of say is that this is just as easy to do in MATLAB, of course, right? So the top there is code for creating a polynomial kernel, or rather, sorry, using a polynomial kernel to make predictions on our test data set. So let me sort of go through that little bit by bit. Here we're going to use degree 6 for our polynomials. That was sort of a reasonable degree if you look for at least the problem we're talking about here, predicting peak demand from high temperature over all the days of the year. Degree 6 kind of looked okay, right? That was sort of, if we got like degree 10 or degree 20, that would start to overfit, but degree 6 looked okay. We're going to use degree 6 here. Lambda is equal to 1. You can try out different values of lambda. You'll actually do a little bit of this in the homework, so you'll try different things out. But then this one line here forms our kernel matrix. So that's actually an important line. So remember, our kernel matrix, this big matrix K, Kij is equal to the kernel between xi and xj, which equals, in our notation that we're sort of using for xi and xj here, it's going to, or rather for our definition of this particular polynomial kernel, this is going to be 1 plus xi transpose xj raised to the d. Right? Now, in MATLAB, you could form this matrix here by doing a for loop, you know, and saying for I equals 1 to m, and then for j equals 1 to m, kij equals 1 plus xi, well, x, like, let's see. So remember, x, our big matrix x here had the rows. Its rows were the different values of the x's, right? That was our definition of our matrix x. The matrix of all the input data with the things as its rows, importantly. So I guess this, let's see, xi transpose would be big X, row I, all the columns, times, let's see, times x, j, all the columns here, tick. I'm not used to writing MATLAB code on the board, but times xj transpose, and then we'll do that for each one. So we could do this, right? That would construct the kernel matrix. But hopefully, and this is kind of the art of MATLAB in some ways, is that typically MATLAB, when you use for loop like this, is not the most efficient. It's an interpreted language, so doing this kind of wastes a lot of time. And it often can be much easier to compute these kind of in one go. So what I'm doing here is I am saying, okay, K, this is sort of try one. The second try is just to say K, the big matrix K, equals 1 plus x tick, x times x tick, I guess. Is that the right order? Yes. Dot to the d. All right, does everyone understand why these two things are, in fact, equivalent? So this matrix here is the matrix of all possible inner products. That's just definition of matrix multiplication, right? So the items here will contain all these inner products. It'll be in, what size is this matrix, actually? Yell it out. M by M, right? So this product here is an M by M matrix. It contains the inner product of each example times all the other possible examples. It's also symmetric, because this should be obvious that it's symmetric. Now, so that's like every single term here. Oh, I didn't raise this to the D. Okay. Now we take every single term here, and we do this thing what you can't do in matrix math, but we can do in MATLAB, which is add 1 to everything. So 1 plus this adds 1 to all the entries here. And finally, we take every one of those things and raise it, element-wise, raise it to the dth power. So this is the same as computing all of these things. It is just doing it all at once. OK, now we have our K matrix. We take the next line there, says alpha equals K plus lambda times I backslash Y. We used the backslash before for the least square solution. Yeah?
Sorry, there's no, I mean, is there an easy way to get smarts and just automatically symmetrize the matrix? Like you're looping through everything. Right?
Yeah, I guess you could only do the first ones of these and then copy the other ones to the thing. But I mean, you should do this anyway in practice.
Right, and then but MATLAB is not smart enough to. There's no other way to do it, right?
Yeah, so it won't. No, typically will not be intelligent and only compute these once and then take the. You know, a smarter linear algebra package would automatically just compute half the entries here and then take the other half as the lower triangular portion. Strictly lower triangular portion, say, and compute only the upper triangular portion. You don't gain that much. I mean, at most you gain, you know, a power of a little less than 2, which is good. It's not nothing sort of to sneeze at. But typically, actually, when it comes to matrix multiplication, a lot of what or really it's not MATLAB, it's the algorithms behind MATLAB. They're very heavily optimized for matrix multiplication. They do things like really exploit the cache of the machine properly, exploit data locality. They're incredibly well optimized, such to the point where if you just wrote your own little for loop that computed this and only computed half the elements, it would probably be slower than the matrix multiply that you actually have here. So you could alternatively try to optimize, you know, cache hits, all this kind of stuff for a symmetric multiply. People have done that, and they'll certainly exist. Some more complex matrix packages will actually represent symmetric matrices only with their top triangular portions. They won't even bother representing the other half, and so then it can automatically do things like that. But the win you'd see actually in MATLAB, if you try to do that, would be small, so it'll just multiply them all out. I think. I don't. I really. I don't. It could be wrong there, but I don't think it does anything intelligent there. But it does something certainly much more intelligent than this for loop. That would be very slow. Okay, so that forms the next line there, the alpha backslash Y. That forms that computes the optimal alphas. One thing to notice here is I'm using the backslash, and before I sort of said the backslash is this code, right? So before we did something like phi backslash Y. This was for theta, right? And I said this was code for phi transpose phi. I'm mixing up my MATLAB and the actual notation here. It was something like the inverse of this thing times phi transpose times Y, right? I said this for linear for least squares. This was the case. Okay. So I'm using it here differently, right? What size is this matrix? This one I'm doing a backslash. Well, first of all, what size was phi? What size is phi always? How many rows is phi? Yes, m rows, one for each example. How many columns does phi have? Yeah. So phi is m by k, so it's not even square. You can't invert it. Don't ever write the inverse of a non-square matrix. But I can still do this, because it was sort of what it's really doing is what this is really doing is phi transpose phi inverse times other things. Of course, how big is that matrix there? Right? The K matrix. What size is it? Right, it's m by m. So K plus lambda I backslash, and I'm again kind of abusing notation here, but this thing is, well, let's just plug it in what sort of, I've said it what it is before. What that really would be then would be k plus lambda I transpose k plus lambda I inverse all times k plus lambda I transpose y. So that thing should really be this, right? By what I've told you before. But in this case, this thing is m by m. And actually, you know what else? It also happens to be invertible. If you have two invertible matrices, sorry, it's the inverse, not the transpose, but the inverse of this whole thing. If you have two invertible matrices, rather two matrices that are both invertible, multiply them by each other and invert the whole thing, the inverse there would be just the inverse of both these things, right? So this is going to be equal to k plus lambda I inverse, k plus lambda I inverse. These are also symmetric, I should add. So there's no, you can just take off the transposes here. Times k plus lambda I times y. But of course, these things just cancel out here, right? So you just have k plus lambda I inverse times y, which is what we wanted. So the long story of that is that for a square matrix, backslash is just going to do the inverse. For a non-square matrix, the backslash will find the least squared solution. That's the short of the story there. And by the way, MATLAB will do that intelligently. MATLAB definitely will optimize that one. So it solves it differently depending on whether that is square or not, and actually also depending on whether or not it's symmetric. So if it's symmetric, it will also use a slightly different technique than if it's non-symmetric. So MATLAB will be smart there, certainly. But also, by the way, this is much faster. If you want to compute this, if you want to compute alpha equals k plus lambda I inverse times y, this is much faster to say this thing backslash y than it is to actually say this thing inverse times y. This essentially boils down again to the fact that it is easier to solve a linear equation than it is to explicitly compute an inverse. As a constant times, it's not sort of a, it's not hugely worse, but it's certainly a little bit worse to actually write the inverse out. And numerically, actually, also, you get more like floating point errors if you write the inverse out like this. But in math, we'll just write the inverse out like this because it's exact in linear algebra math. All right. And now, this is code to compute the prediction on a testing example. So this does the same trick to compute this kernel between the test example and all the existing examples. So remember, our thing we were talking about here, the way to form a prediction on some new example, I guess I'm calling it sort of x test here as our new example. The way to form a prediction on this, remember, is to take sum from I equals 1 to m, alpha I times the kernel between xi and x prime, right? What this line here does, in much the same way as the other line, is it takes the inner product of our example, x test, times everything else, forming essentially a matrix with all of these as the rows of the matrix. And then it multiplies it by alpha to do that linear combination there. So this thing here, these two lines are just this. It's just, again, the sort of the more efficient MATLAB way of doing it rather than writing it out term by term. And by the way, you can do the same thing for the Gaussian kernel. It's all exactly the same. You just use a different computation for k. Here I'm using actually this squared dist function, which takes the square difference between all the possible inputs and makes a big distance matrix. The code for that's with your, you'll use that on the homework, but I include the code for that in the homework. It's like one line of MATLAB code, but it's useful just to have rather than try to think about how to do that in MATLAB. All right, are there any questions here? Because actually this is an important slide because it's equally important to sort of know that you can do a lot of these things in MATLAB without a lot of for loops and to do the sort of compact versions of these code. That's sort of important fact. Just like with least squares, we just said phi backslash y. We didn't, solve for every element of theta individually or something like that. We can do this pretty efficiently too. Or at least compactly written in MATLAB. So here's what it looks like. And as you probably would imagine, it looks a whole lot like what we did with the explicit features. So we happen to not be forming them right now. So for example, the top left here has a polynomial kernel of degree 4 with lambda equals 0.01. This one is lambda of degree 10. A polynomial kernel of degree 10 with lambda equals 0.01. For small lambda, it has actually a pretty small effect when, in this case, lambda can make a big difference in some problems, but here it actually doesn't have that big a difference. Here is the same thing where I'm actually changing the bandwidth on the Gaussian kernel. So if the bandwidth here is very big, that's actually one's relatively small. The bandwidth is very small. It means that the kernel will sort of fall off very quick. It will fall off very quickly because you're dividing by a smaller number. So so remember that the Gaussian kernel is this: k xi xj equals exponential negative xi minus xj squared over 2 sigma squared. So if sigma is relatively small, this whole thing is big for points that are not that close, right? It'll sort of be very big. And negative exponential of a very big thing goes to 0 fast. So basically the kernels will be 0 for points that are not too far away, or that are even a little bit far away. It'll be close to 0. And what this sort of intuitively corresponds to is kind of points that are they're reasonably close by, but not right next to each other, don't really exert too much influence on each other. So the function kind of can go up and down a lot because this bandwidth is very small. It sort of is in your predictions, you ignore all but the points that are very, very close to your input point. If we make the bandwidth bigger, say 40, you get a fit that seems much more natural here, right? Because now what's happening is that this thing is falling off much more gradually, right? Because this thing is much bigger, so this whole term will be smaller. That makes this term bigger. And what that means is points will influence, that the prediction right here, which is this red line here, is actually influenced by a whole lot of these points. And that ends up having the effect of kind of smoothing the function out a lot more. So by the way, for the Gaussian kernel, one way to prevent overfitting is not just the lambda parameter, but also this bandwidth parameter. That's also sort of, because actually you can't change the number of RBFs with a Gaussian kernel, right? It's actually infinite no matter what. But what you can change is the bandwidth of the radial basis functions. The effective radial basis functions, remember. It's sort of as if you had an infinite number of them spread all over space. All right, this also, I should say, works in higher dimensions. So here is that graph I put up the first time of high temperature on one axis, hour of day. I guess it's inverted now, but hour of day from midnight to 24 hours, back to midnight again. And you saw this interesting behavior in both dimensions, right? So an hour of day, you kind of see it go up in the middle of the day and come back down. In temperature, you saw what we saw before, right, where there's this sort of higher temperature. As the high temperature gets pretty low, it'll maybe be on this, or after this is just actually the temperature at that time of day. So not high temperature, but as the temperature gets low, it'll go back up, but then it goes really kind of spikes a lot when the temperature gets higher. This, I believe, is the graph of radial basis functions. So I used 5 radial basis functions in each dimension, evenly spaced, computed the least squares solution to that, and you get these sort of, this is a pretty complex fit to this function, right? But it looks reasonable. I mean, it's sort of finding the right shape of a lot of these things, especially with a lot of data. It seems to be. I mean, I can't get it all perfectly because there's some just natural variability, but it fits it pretty well. One thing you also might notice is that in certain places, it looks like it's kind of bad, right? So look at the top corner there. for some reason up here, it thinks that it goes way up at midnight on a really high temperature day. This is due to the fact that we never see a very high temperature at midnight, right? It's pretty unlikely to have the temperature, at 100 degrees on midnight. And so there isn't much data sort of in this whole area over here. And because of that, it doesn't really know what to do there. So it actually uses sort of funky parameters to make everything else fit better because there's no notion of actually trying to perform well. And there's no examples there. And this kind of, this speaks to an important point in machine learning too, is that in all these things, the functions look reasonable over the data I'm plotting, but that doesn't mean they're going to be reasonable on entirely brand new data outside the ranges ever seen before. I mean, machine learning can be very good. Sometimes when you have high-dimensional functions, you can find nice regularities that actually will make it good in something it hasn't seen exactly before, certainly. It's more than just kind of interpolation, certainly. But there's still a sense that if you saw, if somehow we had some catastrophic event and the temperature was 120 in Pittsburgh one day, I don't know if this sort of line continuing up would really say much about what was actually happening. In fact, what this line looks like over here is actually quite different. This is something like this here, right? It actually just like drops down. It looks better here for a little while, but actually pretty soon it will have a similar effect. So it will just like drop back down. Because there's just no data here. There's no need to do anything intelligent over there for minimizing a loss function. So when we're completely different from the examples that we're given the thing as training data, we're not going to expect it to perform that well. And a little bit more, slightly more theoretically, one way to say this is that the machine learning algorithms expect the examples we evaluate to be drawn from the same distribution as the examples we trained the model on. So that's really sometimes what it's really kind of going to do well on are things that we trained it, or things from the same distribution as we trained it on. Okay, so last bit about kernels here. And that is to say that kernels can also be used with any other loss function too. So I just demonstrated the least squares loss function with regularization, how you find the alpha for that. Okay, but that is by no means the only loss function we can use, right? We went a lot through the class 2 times ago, last week, on how do we compute theta in the explicit feature case. How do we do that for different loss functions? And kernels work exactly the same. In fact, it's not even hard to do this with kernels. All you have to do is this same substitution, this fact that theta here equals phi transpose times alpha. Right? That gives you everything in some sense. It can be sometimes a little harder to actually solve the problem, by the way. To actually convert the problem to standard form or maybe to solve it. But remember, we're going to be using this library called YALMIP, this optimization library called YALMIP. And so it turns out that actually in that case, it can be quite easy to do this. All you have to do is substitute in this thing. So let's say that we want to minimize phi times theta minus y, the L1 loss. Remember, that's the sum of the absolute values of all those different things. We're going to minimize this over theta. Well, this is equivalent to just plopping that in here and minimizing over alpha of phi transpose alpha minus y1. Actually, let's add a regularization term too. What should this become, actually? What should I write here? What's the LT? No, sorry, LT squared. What does this equal in terms of the alphas? So alpha transpose what? V? Phi. Okay, alpha transpose phi alpha, right? And what is that equal to? I guess in both cases, what's this equal to?
Yeah.
Right. So this is equivalent to then k alpha minus y 1 plus lambda alpha transpose k alpha. These things are all computable now, and alpha is a vector of size m. So this is all finite dimensional. It's not even, I mean, I didn't do anything at all tricky here. It's the exact same substitution I did before. I'm just leaving this as an L1 term and saying, we'll solve it with the element. That's what it's doing here. I'm actually not even adding the regularization in this case, but that's what this is doing. Okay, so just like before, really with any loss function, we can just plug in our definitions here. And because our function is always going, the vector of all our predictions is always going to be phi transpose theta, sorry, phi times theta. And our theta is always going to be phi transpose alpha. This substitution will work for any real loss function you have. There are some things you can't do, though. For example, I still want to say this. OK, if you haven't seen it before, please ignore it. It's not. Don't let it confuse you at all. But if you have seen it before, this is one interesting thing. So one thing people do sometimes is that rather than optimize penalizing the L2 norm of theta, you can penalize other norms of theta. For example, you can penalize the L1 norm of theta. And that would actually be putting a penalty on the absolute values of theta rather than their squared value. So that's actually a very common thing to do. It's a very sort of hot topic in machine learning as well, because this actually encourages, and again, if you haven't seen this before, don't worry, but this actually encourages the solution to have a lot of zero values in theta. So it results in what's called a sparse theta. So this is something you might want to solve. OK, I'll just leave it at that. Unfortunately, unlike the L2 norm, where we sort of were saved here because the L2 norm squared is just theta transpose theta, and we could place the case with that, there's no real way to penalize this thing in the expansion here. And in fact, the Representor Theorem that I mentioned before doesn't actually hold anymore in this case. So importantly, let me go back. Representative Theorem says only when we regularize with the L2 norm of lambda is this thing true. So we can't do this. We can use other loss functions, but we have to use L2 regularization when we talk about kernels. You can do a couple other things, like you can use sometimes penalize this. I think that can work as well. But we're just going to always talk about using the 2 norm squared as the regularizer there, because that is equivalent to this. And we can always write that down. And that's actually what gives this representative theorem too. OK, so that was the end now of nonlinear regression. And I think this is actually one of the conceptually hardest lectures in the course, because what these kernels are is really kind of confusing. Certainly the first time you see it can be very confusing. So good job getting through this far. Yeah?
How will we construct the big X matrix?
The big X matrix here is, well, first of all, you don't really need to do that, right? Because, I mean, well, you do in forming the kernel. So that's this thing here. That's this here, right? OK, so the big X matrix is X equals X1 transpose, X2 transpose, all the way down to XM transpose. That's just the definition of big X. Just like big phi was the feature vectors here, phi of X1 transpose, phi of X2 transpose, etc. Phi of XM transpose. The X matrix is the same thing with just X's. But remember, X here, even when phi is really big, the assumption is that X is not too big to form this. So X is, remember, Xi is a vector in Rn, whereas phi of Xi is a vector in Rk. OK? So n here, I mean, examples we've seen mainly n equals 1, right? N is just the one high temperature input. in the 3D examples now, here x is 2. X is an R2, so n equals 2. Our inputs are temperature and hour of day. So the point is that we sometimes want to use very high dimensional features, k, even when x itself is very low dimensional. That's how we actually capture these nonlinear functions, right? In the case of linear regression, phi just equaled x, or it equaled x and plus a constant term. So those are sort of on equivalent terms. But in general, your features here will be very different from your inputs. So the inputs, we can store this matrix, format and store it pretty easily, even if these things are very big. OK, any other questions on this last bit of nonlinear regression? And the homework, you'll have to do two things. First of all, solve these with a kernel. And secondly, you'll also want to actually see if you can write this in that other form we talked about, which had explicit, in the form where you could plug it into a linear programming solver. So you'll have to do both of those for the homework for these here. For the 884, the second one is just for 884. The first one is just for 484 as well, though. OK, so with that, this is all the material covered up to the first homework. So now you have everything to do the first homework. But as I said, and I should say that the lectures, the notes, everything that you need to do the homeworks are in the slides and on the lectures themselves. Lectures are all video recorded, so you can watch them. You can sort of fill in. If you can't remember a certain point, you can go back and try to watch it. I guess I'm just putting the videos on kind of raw. If people want to tag certain places where I say certain things, that's fantastic. Send me, do that on YouTube or whatever, and then you can even send me a mention that you did that, so I can publicize it. But hopefully you can go back and find the spots where I talked about different things in the lectures. So let me now talk about the next subject in the class, which is classification. All right. Now, as I said before, classification is actually very similar to regression. A lot of introductory texts will treat this very differently and say classification is completely different because you're talking about, and they talk about different algorithms for it and different everything for it because you're talking about now discrete valued outputs rather than continuous valued outputs. That seems completely different in some ways. We're not going to do that. We're actually going to use almost identical algorithms to deal with classification as we do with regression. The only difference is that the output, rather than being, I'll say this more formally in a second, but the only real difference is that regression had our outputs yi's. Those were real valued. Classification, they are discrete valued. Say 1 to k, or even one thing we'll deal with a lot is binary classification. And in that case, yi will be, I typically use -1 and 1 to talk about the negative class or the positive class. I'll say this more formally in a second, but that's the only difference. And you might say, okay, well, this seems pretty different. Just think about this one for a second, actually. Let's not worry about this one. This seems pretty different, right? Because you can't, theta transpose phi is not going to always be either -1 or 1. So that seems different, right? You can't just predict theta transpose phi. That's true. But by the way, all we're going to do is look at theta transpose phi and take the sign of that. And that becomes our prediction for this case. And that's actually a very... Let's do a couple other differences too. But actually just doing that gets you pretty far. If you were to just treat it completely the same, use +1 and -1 as your outputs, and use these squares, that's actually a pretty reasonable approach. That can work pretty well. Can also fail, but it can work pretty well. All right, so that's a little intro, but what I'll actually talk about in this section is both examples and then also algorithms for the slight differences between classification and regression. So I guess I actually even said it here. I should have just gone to this slide first. So again, classification, predicting continuous value outputs. Regression, continuous value outputs. Classification. In our case, we'll talk actually just about binary classification. And that has just -1 or 1 outputs. For people that want to do like a project or something like that with more types of outputs, there's some very simple extensions that can extend from the binary case to the case of having k different variables that you're trying to pick between. All right. So as I said before, in binary classification, things have you can think of these as being yes/no answers, right? The outputs are either +1 or -1, kind of yes or no, right? So for example, you could take certain things, and this is actually, the first one I have here is actually kind of an odd case, but it's actually an important case too. So the first question we might want to ask is something like, will the peak demand be higher than 2 gigawatts tomorrow? So before, what we were doing is we were looking at high temperature and predicting what the peak demand would be. Right? But what if we don't really care about what peak demand, the actual peak demand? All we care about is if it's going to exceed some threshold. This is actually a very important problem for planning purposes, right? Because oftentimes what you'll do is you will plan your generation accordingly, maybe a couple days ahead or a day ahead. And then you want to know, kind of maybe a little after the fact, after you've scheduled these things already, well, am I going to exceed my planned capacity or not? That's a yes/no question. And by the way, that sort of yes/no answer might be the thing that matters most to you, right? You don't really care how much you exceed it by or how little you exceed it by. You probably do care about those things, by the way, in practice here, but just for the sake of the simple kind of thought experiment, think that you don't. I don't care, how much am I going to exceed things by. All I want to know is, am I going to exceed it? And if I exceed it, then I have to maybe replan everything to make sure that I have the right amounts. Maybe I'll do something like an electric line too. That's sort of a simpler example of the same thing. But electric lines, as we'll see in the next unit in this course, have a capacity a lot of times. They can't transmit more than a certain amount of power. That's what they're rated for. And if they start doing more than that power, physically will happen. They'll start to heat up and eventually sag and then maybe melt or catch on fire or something like that. You don't want that. But what happens in practice is that because of that, people have a certain rated power for these things and say, okay, up to this power, they can transmit. More than that, they can't transmit. Right? So in this case, what we care about is, will the power across that line be more than the rated amount? If it's more, we care about it, right? That's a bad thing, because we don't want it to be more than that amount. We don't really care by how much. The line's already melted. And if it's less, we don't care how much less. It could be 0 or it could be right at that amount. We're going to say we don't care. It's rated for that amount. We're just going to do it. So here's an example where we don't really care by how much we exceed or by how much we are short. All we care about is the answer to that yes/no question. And finally, something even more like in a home. This is actually a subject that I do a fair amount of work in, analyzing energy data in homes. Is this device that just turned on in the house, for example, a refrigerator? That's a yes or no question, right? We can't say 0.1 to that. That's not the right answer. We want to say yes or no. So these are all examples of kind of yes/no questions that we might want to answer as yes/no questions. And in fact, even if, as I was saying before, even when, in some sense, we're really predicting a numerical quantity, what we might actually care about is the answer to a yes/no question. So even if the transmission across that line is still a number, we might really care more about the yes/no question. And this is a more subtle point, so don't worry if you don't quite get it yet. But it turns out that if we really care about getting those yes/no answers correct, we're often better off thinking of it and solving it as a classification problem rather than solving it as a regression problem and then just sort of looking at the regressed result and sort of looking at the predicted result and seeing that it sees it or not. The answer to that is that because, and this is a little bit hand-wavy, but We'll get to this in more detail. Essentially, regression treats all inputs as being the same. So you want to minimize your loss on everything, right? What that means is it's going to try to get kind of going to try to predict the point well at every single point. So say we have some range of possible inputs, and right here, something bad happens. Actually, I should draw it like more like this. Say we have this is our input. This is our output. So this is, I don't know, some features, and this is, how much power is going over that line. And maybe it looks something like this. I don't know, something like that. And right here, something bad happens. Okay? So it's a pretty simple, actually, function, you could say. So basically, if the input's higher than this, something bad is going to happen. Otherwise, it's not going to happen. If you try to fit a line to this, though, it might actually kind of basically, it's going to linear regression will try to fit this thing well everywhere, and so it might draw you some line like this, or something like that. If this goes way up, right? In which case, it's actually not giving you the right threshold about when things are going to go bad or not. So sometimes, even when the answer, or even when you're talking about some numerical quantity, it still is better to think about it like a classification task. We'll come back to this. Don't worry about this too much yet. This is sort of more of a foreshadowing what we're going to talk about later. We'll come back to this when we talk about loss functions for classification. Just like with regression, we have loss functions. We'll also have loss functions for classification, and they'll capture exactly this kind of intuition here. So, all right. So let me start off now by giving an example. And this is, as I said, something that I work in a fair amount. We're not going to quite cover the fully complex case here, but I'll just introduce what's going on here, and then we can wait till next time to actually cover it. So first of all, what I'm going to talk about in this section, the motivating example last time, a motivating example, that of course regression is applied everywhere, and classification is applied in a huge number of domains, well beyond power systems too. They're applied all over the place. But I'm using examples from power systems and the smart grid. The running example we had with regression was predicting what electrical demand is going to be given high temperature. That was our kind of running example. And I could use that same thing, by the way, for classification. I could use, is it within a certain range, or is it going to break some amount? That could be perfectly good too. I'm not going to do that. I'm going to use an example from building systems. And buildings are fairly important, actually. I was talking about the sort of, in the very first class, I talked about what different things consume what amounts of energy in the US. And at least for electricity, buildings, that's commercial and residential, account for about 70% of electricity in the US. So buildings are actually probably, everything's in buildings, right? In some sense, we all spend a lot of our time in buildings. And they account for a very, very large portion of the US electricity consumption. One task that's so not only do buildings consume a lot of electricity, right now, very little is really understood by the occupants about what they are actually consuming. Right? So this building is using all sorts of energy, but how much is being spent on lighting and how much is being spent on air conditioning? They might know that here. The facilities management might know that here. They might not. I certainly don't know that. And it turns out that, and I don't know for this room, for example, how much more power do I consume by turning on the lights here so you all can see better versus just opening the windows up, but that would affect the videotaping quality. I don't really know actually how much I save by doing that. And it turns out that this not knowing is actually a big deal. And if people understand electricity better and provide them more information, they tend to actually cut their energy a little bit. And so understanding the consumption in buildings and giving people feedback about this is actually a very, very powerful technique that we have at our disposal to increase efficiency of buildings. It's really not the only thing. We're not going to get it to zero that way. We're not like we're going to make people so efficient they just use no energy at all. But it's very important in kind of the big picture to think about how we can actually give people better feedback and give people more information about their consumption. Now, the example I'm going to have today is about detecting an appliance. And it's actually a very simple case. It basically says I'm looking at some power signal from an outlet. So I'm going to say that I'm going to put a plug monitor on that outlet. I don't know what appliance is behind it. I'm going to put them on everything. Maybe when we build a building, we just build them with sensors on every outlet. And then I'm going to ask the question, what was this device? Or more importantly, in the simple case, for the binary case, was this device that just turned on this outlet? Was it a refrigerator, say, or not? That's the kind of question I'm going to ask. Now, it turns out that similar techniques can actually be used to do very similar stuff even without those plug monitors. So it turns out you can also do very similar things if you just look at the power monitor of the building. But the example we're going to talk about is this sort of more simple one of detecting, given a plug signal or a plug's power trace, what is the appliance? Boy, how much time do I have? You know what? I'm going to actually stop here because I only have 5 minutes left. So next time, I'll start with this classification example. Maybe I'll probably end up motivating it again, but I'll spend less time motivating it again. And then I'll talk about what our example for classification is going to be, and whether or not, going to form as a classification problem, and then look to see what's a more formal setup for classification that is very similar to regression, but lets us sort of actually answer these yes/no questions. So, are there any questions about this or this introduction here, or the material from the main portion today? All right, in that case, we'll meet on Thursday. Download the homework, by the way.